Hello and welcome to Lesson 3 of Python for Musicians, a Python tutorial series aimed at musicians of all levels. I have to say I'm really excited to be filming this lesson because we are finally getting into the music portion of our series. Up until now, we've seen how to set up our environment in Lesson 0. We've had a look at arrays and lists in Lesson 1, and we've learned about the sine function in Lesson 2. By the end of this lesson, we'll be generating audio samples purely from code, which you can use in any way you like. Here are some examples that I've generated. So the plan for this lesson will be as follows. First, we're going to talk about some digital audio fundamentals and what we need to be careful of. And then we'll jump straight into Python and start importing audio files, outputting audio files, and we'll have a quick look at the possibilities that we have unlocked. So let's talk about sound for a bit. Sound is a pressure wave. What our ears pick up as sound is actually the transition from different air pressures over time. Sometimes the air pressure is high and sometimes it's low. And the frequency of that change is what we perceive as musical pitch. To translate this into digital audio, we can assume that the waveforms we generate are analogous to the speaker driver's position, itself analogous to the pressure around our ears. The nature of audio being digital, however, means that we represent audio signals by a series of data points sampled from a continuous absolute. The reason this is so is because we need to store information about the audio wave. And this information takes up computer memory space, and the more there are of these points, the more we need to compute. So when digitally recording the real-world sounds with a microphone, for example, we're storing the microphone's displacement at regular intervals of time, or at least that's how we can understand it. The sampling frequency is the number of samples that we take per second of audio. That's also known as the sample rate. The sampling period is how often a sample is taken. They're inverses of one another. When we generate sounds from scratch in a computer, we're actually predicting the theoretical output of that wave and sampling that. As an example, this is a continuous sine wave that we'll sample. And this is what that sampling will look like. The red points here are sample points that our computer will interpret. Notice that the grid lines show a sense of horizontal or temporal accuracy and vertical or amplitude accuracy. The horizontal or temporal accuracy is determined by the sampling rate or the sampling frequency. And the vertical accuracy is determined by another parameter known as bit depth. Without going into too much detail here, most audio formats hold these numbers as integers, and the bit depth is essentially how many bits are used per sample. We'll be dealing with floating points in our processing, and don't need to worry too much about bit depths. We care much more about the sampling rate, because that's a parameter that we'll be using all the time. This is what it would look like if we sampled less often, with a lower sampling rate. Notice how the red points are spaced out a bit more in the temporal side. You can imagine that if our wave was a little more complicated than just a sine wave, it would be much harder to represent. Also, you can imagine how with higher frequencies, we'll be able to represent them with less fidelity. Conversely, this graph here shows bad bit depth. Again, notice how the red points are further away from the true wave, but this time on the vertical side. While the bit depth also has an effect on the accuracy of sound wave representation, it doesn't discriminate between higher and lower pitched sounds. This graph here is just included to show what really bad sampling looks like, bad sample rate and bad bit depth. Let's now play some sound examples with different sample rates. Notice as the more we lower the sample rate, the more mushy the sound gets. That's because we lose the high frequency detail that makes the sound crisp. This is some Chopin that I recorded a while back. Okay, so we're now in Python. I've gone ahead and done the usual steps to get started. So I've created a new folder inside Python for Musicians called Lesson 3. And inside that folder, I created a new Python file called audioio.py. I've also opened our terminal to that folder and activated our Python for Musicians Conda environment. The first thing we're going to need to do to import and export audio files via Python is to install a few libraries that will do this for us. The main one that we're going to install is Librosa. We're going to install Librosa because it also comes with extra additional files and things that will be useful for us in the future. So to install Librosa, we need to type conda install as usual. The way to figure out what the installation instruction is typically from the documentation page of that library. So in this case, we need to type conda-forge and then double-colon Librosa because it doesn't come standard with the Anaconda package. We hit enter. It's going to tell us that it needs to install a couple of other things, which is normal. We say yes, and this should be done fairly quickly. So let's go ahead and import what we need into our Python file. So the first one we're going to import is NumPy as np. Then we're going to import Librosa, just as Librosa. We don't really care to change it to anything else. And let's also import Soundfile, which is a library that Librosa has installed for us. I'm also now going to specify a project sample rate that is a global parameter, just like so. So importing audio into Python using either Librosa or Soundfile will import it as a tuple. So it's worth getting familiar with tuples from now, as we'll be seeing them over and over again. So a tuple is a collection of variables, and they are defined either like this or like this. And accessing their elements is very similar to accessing elements of a list. So here, for example, the first element is, this is a tuple with the square brackets and 0. Again, same as a list. So the first element here represents 20 as an integer, and the second element here is 5. So if we go ahead and print these, that is what we expect to see. A neat shorthand that we can do with tuples is to unpack a tuple like this. So first element, comma, second element is equal to the tuple that we have defined. This one line of code here does the same as this. So how does loading audio in work? When we load in an audio file, we're actually loading a tuple. So I'm going to just for now call this an audio tuple. And I'm going to go ahead and paste in the default settings of Librosa's load function. So librosa.load takes in a couple of arguments. The first argument it takes in is the relative path to a music file. In my case, I've got an audio file called piano.wav in lesson 3, and it's right there next to audioio.py. The second thing that librosa.load takes is a sample rate notated as SR. And you'll see here that the default sample rate, if we don't specify anything, is 22,050 Hz. This is half of CD quality. If your plans are simply for analysis purposes, then this may be good enough and save some space in RAM. But if your plans with this audio file is to process it with effects and things like that, then you might want to specify either a higher sample rate or none, which tells Librosa to use the sample rate of the file itself. The next thing to note is that Librosa takes mono files by default, or rather, it converts your audio file into mono by default. This is not necessarily a good or a bad thing, it's just something that you need to be aware of. The next parameter it takes in is an offset parameter. This tells Librosa at what point in seconds do you want to start loading your audio file in. Say, for example, you know for a fact that your audio file has about 5 seconds of silence before anything meaningful happens. You can say offset equals 5 to start loading in at 5 seconds. Duration does something very similar to offset in that it's, again, the duration of the audio file you'd like to load. So say your audio file again is about 30 minutes long and you only want 15 seconds of it. You'd put here duration equals 15. The last two parameters here we don't need to worry about too much. The first one is the data type of the NumPy array that will be created. By default, it will use NumPy float 32s, which is more than fair for our audio processing tasks. But if you want extra fidelity and your audio file has a high bitrate, then you might want to use float 64 instead. And this res type stands for resampling type. And by default, it's this, XOXR. This is the type of resampling that is used by Librosa if it needs to resample your audio file. So what is this audio tuple then that librosa.load is importing, I hear you ask? Well, this audio tuple can be opened into two parameters. The first one is the wave data as an NumPy array, and the second one is the sample rate. So if here you've specified a sample rate, or you have kept it to be the default value of 22,050, this sample rate here is going to equal this. However, if in here you have none, then this sample rate is going to be the sample rate of the default audio file. What I would do if I was using Python for these kinds of applications would be to have a default project sample rate, and then any file I import, I'm going to use that same sample rate. So what I would do here is I don't really care about most of these things. And in here, I'm just going to say project sample rate. So as this wave variable is a NumPy array, it has a shape property, which we can print out. So if I were to print out this shape, after taking a while, because this is the first time that we're running Librosa, it should give us the shape of our wave array. And this piano.wav is a long recording, so it should be quite a few samples long. And here it tells us that it's this amount of samples long. We're not going to cover different ways of processing these wave files just yet in this lesson. We're going to focus more on creating sound files in Python to then bring out. So the way we're going to be creating these audio arrays that we'll be converting into audio files in Python is to first start with a time array, an array that keeps track of time, and then apply transformations to that array to get the sound out. So let's see how to create this time array. The first thing we're going to need is to determine the time in seconds of our time array. And I'm going to give this value of 2 for now. The next thing we need is to get this time in seconds into the number of samples that the time array will need to be. And that can be done by multiplying the time in seconds by the sample rate. So time in seconds times project sample rate. I'm actually going to redefine the sample rate over here so that it's easier to see in the rest of this project. Now, an important step here is to make sure that the time in samples is always an integer. And this is not always the case in this case, because the time in seconds here can be any number of seconds. And if that number, when multiplied with the sample rate, doesn't make an integer, we're going to have a problem, because we can't have a floating point number of samples in an array. So the way to do that is to just put the whole thing inside an int function, int, which of course is an integer. And this will round down whatever this number is to the nearest integer. So let's create our time array. So time array is equal to, we're going to use the linspace because we want linearly spaced values. We want the time to start at 0, and we want it to go all the way up to the time in seconds. And we want this time array to have the time in samples number of samples. Finally, and I'll explain why we need to do this in a second, we need to specify that endpoint is false. It's crucial to understand why endpoint must be false here. It's perhaps easiest to see why by seeing what happens if you try and generate another vector, perhaps one worth 5 seconds, both without the endpoint condition, to see what the problem actually is. So these two arrays here are time arrays, one worth 2 seconds and one worth 5 seconds. And notice that I haven't put the endpoint flag here. So let's go ahead and print out the 44,100th sample of both of these arrays. And I've also printed here a equality condition to see whether these two samples are the same. Now, of course, we expect them to be the same because 44,100 at the sample rate of 44,100, we expect that to be the start of the second, or 1.0, because the first second goes from 0 to just about 1, and then the second starts at 1 and then goes to just about 2. You get the picture. So let's run this, and we'll see here that these numbers are slightly different, and they're not exactly 1 either. And this is a problem. So let's just add here the endpoint condition to be false and retry this. We should now get that they are both 1 and that this is true. So now that we've got our time array, let's build upon what we learned in lesson 2 and create a sine wave out of this time array. So let's say that the sine wave frequency should have a value of 200 Hertz. And let's give the amplitude of this sine frequency a gain of 0.2. I've gone ahead and quickly reorganized the code here so that it's more readable. And let's create our sine wave now. So let's do sine wave is equal to np.sine. And then in here, we're going to need to give it 2 times np.pi times time array. And finally, times frequency. Now, before we listen to this, we need to be very, very, very careful. We always have to make sure that we multiply our sine wave by a gain that is less than 1. And the reason we do this is because it's crucial that anything that we send to our speakers is less than -1 to 1. Anything more than these values are going to start clipping and will be very, very, very loud. As such, there are two rules that we have to respect as music coders. The first is never test any of your code with headphones on, because the smallest error can give you permanent hearing damage, and you don't want that. The second thing is to put a check in your code that will break the code if this condition is not met. This check is going to take the form of a sanity check function that we're going to write, and it's going to take in this sine wave. So let's define this sanity check function very quickly. So define sanity check. It's going to take in a output array, which so I'm going to call this output. And this array is of type np.ndArray. And this sanity check is not going to output anything. So it's going to return none. The sanity check is going to consist of two assert statements. Assert statements essentially interrupt your code if the stated condition is not met. This is how you write an assert statement. You say assert, and then in here now you can give it a condition. So I'm going to say that the output.max, which is a numpy method for these arrays, it returns the maximum number in that array. We need to make sure that this number is less or equal to 1.0. And if this does happen, we're going to give ourselves a message to print in the terminal that says where our code went wrong. So in our case, I'm going to say volume warning audio clips above 1. Similarly, we need to have the inverse of this. So assert that the output.min is more than -1. And the volume warning we're going to give is that the audio clips below -1. Finally, now we can write our sine wave once it has passed the sanity check into an audio file that we can listen to. And the way we would do that is with soundfile.write. So sf.write, and then in here it expects a couple of arguments. The first one is the file name. So I'm going to give this a name sine out. And it can have any extension that's a classical audio file. So it can have MP3, WAV, sound file will take care of that. So I'm going to put here MP3. The next argument that soundfile.write expects is the array to convert into a file. So in this case, it's this one, sine wave. And then finally, it expects the sample rate so that it can tell the file how fast it needs to play the points that it's given. So once this is done, we can run our code, and hopefully, if we've done everything correctly, we should have no problem. Our code should go straight through, and we should get a file in our directory called sineout with all of this. There we go, no errors. And if I list the stuff that's in the directory, we will see right here that we have a file called sineout.mp3. But generating sine waves honestly is a tiny bit boring. So this allows us to get as creative as we want. So let's change some things here. Let's say that we want to create a file that's now 5 seconds long. And this won't be a traditional sine wave. This will be something more complicated. But we can keep it as sine wave settings for now. Let's give it not a frequency, but a center frequency of 330. So that's the E just above middle C. And let's give it a master gain of 0.2. Let's keep our time array as is because this definition works for everything. And let's now build a ramp. So a volume envelope basically that our sine wave is going to be subject to, or rather that our output, final output, is going to be subject to. So let's give it a ramp up time of 0.2 seconds. Let's get these 0.2 seconds in samples, like so. Let's also say that the remaining time of the sound file is going to be ramping down. We can do that by saying that the ramp down time in samples is the total number of samples minus the number of samples of the ramp going up. So the going up portion of our ramp is going to be linearly spaced values from 0 to 1 in ramp uptime samples, endpoint false, and I'm going to give this whole ramp an exponent of 4. And because these values are between 0 and 1, an exponent basically is just going to skew it a bit so that it builds up gradually. Similarly, the ramp down is also going to be linearly spaced values, and then I'm going to give it an exponent of 2 so that it's less sharp than the one going up. And finally, we can create the entire envelope by adding these two ramps next to one another. We can use the concatenate function from NumPy to do this best. So numpy.concatenate, and then in here we need to say the ramp up, ramp down. Let's also create a sine wave to give a tremolo effect to the main audio file. I'm going to give it a frequency of 10, so that's going to go up and down 10 times every second. And the sine wave that's going to control this, I'm going to call it amplitude modulator, so amp mod, and that's going to be equal to the typical way we'd make our sine functions. So np.sine, our time array times the frequency that we expect, times 2 times pi. And then because the sine function goes from -1 to 1, and we only want it to go from 0 to 1, we need to scale this. And the way we can scale it is by adding 1 and dividing by 2. But the order of operations here is important, so we just need to go ahead and add these parentheses over here. Next, let's give it some frequency modulation. So say that our initial sine wave is going to have a different frequency at every point. And how are we going to calculate the frequency at every point? We're going to use another sine wave. In synthesis, this is known as linear frequency modulation. And the more wacky the ratio, the more interesting and bell-like the results we're going to get. The ratio here is the ratio of the frequency modulation, how fast the frequency goes from side to side, essentially, to the base frequency of the sine wave. So let's give it an FM ratio of 1.382, and then how much of the frequency are we going to move? we're going to say that we want a frequency amount of 0.8, so that's 80%. Now we can calculate the FM frequency that means for the ratio. So that's center frequency of our main oscillator times frequency ratio. And then the frequency amount gain, again, is the center frequency times the ratio of the FM amount. And then finally, we can create our frequency array. This is the array that's going to go instead of the frequency number that we typically give here in our sine wave, where this frequency is. We're going to give it frequency array. And this frequency is going to go at a rate of FM frequency, except that this time, the amplitude of this frequency is not between -1 and 1. It's between the frequencies that we want to be shifting. So we're going to multiply that by the frequency amount gain, which we've just calculated, and add the center frequency to this. So let's put all of this together now. Instead of this being just a regular sine wave now, this is going to be our output array. The gain here is going to be a master gain. We also need to multiply it by our gain envelope. So times gain envelope, and by our amplitude modulation envelope. The reason we can do this and not skew away the master gain is because gain envelope goes from 0 to 1, which is a normalized value. And so does the amplitude modulation. So the master gain is acting as a master gain in this case. And then finally, in here, in our sine function, instead of this frequency number here, we're going to give this frequency array instead. And this will only work if the time array and the frequency array are of equal length. I just realized I forgot to put the time array inside this sine function here. But this operation here, time array times frequency array, will only work if the frequency array and the time array are of the same size. And that is the case because the only array parameter in frequency array is time array. So everything here is going to be done on time array and therefore have the same size. It is worth being careful of one thing though. If frequency array and time array have different dimensions or are matrices, so they might have a shape of 1 by 2 or 2 by 1, that can be problematic. But we've defined these with linspace, which creates vectors. And so they are vectors, not matrices. And so the multiplication of two vectors is going to be element-wise multiplication rather than matrix multiplication. Here at the sanity check now, we're going to put the output array instead of sine wave. And then finally here as well, we're going to put output array. Final thing, let's call this creative output. Let's save our file and run it. And hopefully, again, we should have no output here, but a new file inside our directory. So if I list the items in our directory, we have now a creative output.mp3. And this is what it sounds like. I hope you found this lesson useful and insightful. What we saw there at the end was a mere glimpse of the possibilities of programming in music. To get to synthesizer status, however, we need to be able to generate these audio files in real time, and we'll get there eventually. But for now, let's focus on different types of sound making and shaping possibilities. In the next lesson, we'll look at generating different oscillator wave shapes, such as the classic sawtooth, square, and triangle waves. I'm maintaining a GitHub repository of all the code and all the lessons that we are talking about in this series. The link for that is in the description. If you know anyone who would benefit from this series, don't hesitate to share it with them. Also, if there's a topic that you'd like to see covered, let me know in the comments. If you'd like to follow the series and support the channel, consider leaving a like and subscribing to receive the rest of the lessons in your feed. I'll see you next time.